this lecture we are going to talk about what do we mean by weight distribution of a linear block code, and then we are going to talk about how is the error correcting capability and error detecting capability of a linear block code dependent on the minimum distance of a code. So, we will continue basically our discussion on distance properties that we started last time. So, this is one example of a linear block code where number of information bits is 3 and number of coded bits is 6. This is a list of 2k code words, which is 8 code words message bits, and these are their corresponding code words. So, these are the from 000 to 111, these are our 2k message bits, and corresponding to each of these message bits, these are the corresponding code words. Okay. Now, let us look at what is the weight distribution of these code words. So, this code word, this is all 0 code word. So, the weight Hamming weight for this is basically 0. What about this? This code word has 3 ones. So, Hamming weight is 3. This code word has 3 ones. So, its Hamming weight is 3. This code word has 4 ones. So, the Hamming weight is 4. This code word has 3 ones. So, Hamming weight is 3. This one similarly has Hamming weight 4, this one Hamming weight 4, and this one has Hamming weight 3. Now, what is the minimum distance of the code? As you recall, we defined the minimum distance of a code as minimum weight of a non-zero code word. So, what is the minimum weight of a non-zero code word in this case? It is 3. So, the minimum distance of this code is 3. So, let AI denotes the number of code words in C with Hamming weight I. So, if you look here, I will use A0 to denote number of code words which have Hamming weight 0, and that number is 1. Do we have any code word with Hamming weight 1? No. So, A1 is going to be 0. What about A2? How many code words we have with Hamming weight 2? Again that is 0. What about A3? That is basically 1, 2, 3, 4. We have 4 code words with Hamming weight 3, A4, 1, 2, 3. Okay. We do not have any code word with Hamming weight 5 or Hamming weight 6. And you can do a quick check, the number of code words should add up to number of code words that we have, which is 8, 1 plus 4 plus 3. Okay. So, we are denoting by AI the number of code words in this linear block code with Hamming weight I. Now, this set which describes how many code words we have of particular weight, this is basically known as weight distribution of a linear block code C. So, for this block code, the weight distribution is given by this. This completely specifies the weight distribution of this particular 6-3 linear block code. And since we have said a linear block code will have an all 0 code word, so A0 will be 1, and sum of all these code words, they should all add up to total number of code words, which is to the power k. I just worked out this example for the 6-3 code that we have shown in the previous slide, and I showed you that in this particular example A0 is 1, A3 is 4, A4 is 3, rest all others are 0. And I also showed you that the minimum distance of this code is 3, because minimum weight of a non-zero code word in this example is 3. Now, the probability of undetected error for a linear block code over a binary symmetric channel is basically related to the weight distribution of the code. So, for a 6-3 linear block code, and so when does a undetected error happens? An undetected error happens if, let us say, you send one particular code word and at the receiver you receive some other code word. So, without loss of generality, let us assume that we sent a all 0 code word, and at the receiver you received any other non-zero code word. So, if I send an all 0 code word at the transmitter and at the receiver you receive any other non-zero code word, then that will be the case of undetected error. So, you can see basically that is why I have written it as, so what is the probability of, when you are sending an all 0 code word, what is the probability of getting another code word of weight ai, of weight I? What is the probability that when I am sending an all 0 code word and you receive a code word which has weight I? Now, that probability is given by, since we are considering a binary symmetric channel. Now, recall what happens in binary symmetric channel: 2 inputs 0 and 1, 2 outputs 0 and 1, and what is the crossover probability? That is basically given by P. So, with probability P, 0 can get flipped to 1, 1 can get flipped to 0, and the probability of correct detection is 1 minus P. So, you are sending a code word which is an n bit tuple. Now, what is the probability that you are sending an all 0 code word which is of all 0 bits, you receive another code word of weight I. Now, that probability is given by p raised to power I. This will happen when I bits get flipped and n minus I bits do not get flipped. So, that probability is given by p raised to power I into 1 minus p raised to power n minus I. And how many such code words exist? That number is given by ai. So, the probability of getting a weight I code word at the receiver when you send an all 0 code word, that probability is basically given by this. Okay. Now, an undetected error will happen if the receiver receives any non-zero code word. So, I have to sum up this probability for all I going from 1 to n. So, this is my overall undetected error probability if I send a linear block code over a binary symmetric channel. So, for the example that I have considered, I know the weight distribution. So, if I plug that in here, what I get is, so there were 4 code words with weight 3. So, this is 4 p raised to power 3, and what was n? N is 6. So, 6 minus I, which is 3 in this case, is 3. So, first term that I will get is this. the next term corresponding to these code words is given. So, there are 3 code words of weight 4, probability of 4 bits getting flipped is p raised to power 4, and probability of the other 2 bits not getting flipped is 1 minus p whole square. And since p is typically small, I mean I can approximate it for a small p, I can approximate this undetected error probability as 4 times p cube, because this will be close to 1, and since p is a small number, p raised to power 4 will be a small number. So, this will be roughly equal to 4 into p raised to power 3. This is for the case when p is small. So, you can see in general, so in this particular example, the undetected probability basically varies as p raised to power 3, which is basically same as n minus k. In general, we can show that undetected error probability is dependent on how many parity bits that we have. So, more the number of parity bits, lesser will be the undetected error probability. So, we can make the undetected error probability go small by increasing the number of parity bits. Now, if we have a code word with minimum distance d min, we know that any error pattern of weight less than equal to d min minus 1 is not going to change that code word into any other valid code word. So, in other words, if there is an error pattern of weight d min minus 1 or less, then it cannot change a valid code word into another valid code word. What does that mean? It means that we can actually detect any error pattern of weight up to d min minus 1. So, all error patterns of weight d min minus 1 or fewer errors are basically detectable, and this is also known as random error correcting capability of a linear block code. Now, take an example of a repetition code that we did in the first class. So, let us say we have a rate 1/2 repetition code. So, then for 0 we are sending 0 0, and for 1 we are sending 1 1. Now, let us assume because of error in the channel some of the bits got flipped. So, let us say this what we received in when we let us say what we received is 1 0. If you receive 1 0, can you detect? So, what is the minimum distance of first answer this question? What is the minimum distance of this code, this rate 1/2 repetition code? We can see basically minimum distance is 2. Minimum distance of this code is 2. So, according to this, we should be able to detect all error patterns of weight 1. So, let us take an example. Let us say we receive 1 0. Can you detect the error? Yes, we can, because since it is a rate 1/2 repetition code, what we expect is we expect to receive either 0 0 or 1 1 if we transmit this code word over a binary symmetric channel. But what we have received is 1 0, which is neither 0 0 nor 1 1. So, we are able to detect single error. So, to repeat, basically if you have a linear block code whose minimum distance is d min, you will be able to detect all random errors of error pattern up to d min minus 1. Next we are going to show how is the error correcting capability of a linear block code related to the minimum distance of a code. So, if we have a linear block code C whose minimum distance is d min, where d min satisfies this relation, d min is greater than equal to 2t plus 1, where t is an integer, and it is less than equal to 2t plus 2. If d min satisfies this relation, and if we have a linear block code with minimum distance d min, then it is capable of correcting all error patterns up to weight t. So, let us prove this result. Let us assume the code word that is transmitted is given by V, and what we received is the centuple R. Let us assume there is another code word W which is not same as V. Now, we know from triangular inequality that Hamming distance between V and W will be less than equal to Hamming distance between V and R plus Hamming distance between R and W. Now, let us assume that the error pattern has weight t hat, and what is R? R is nothing but V plus this error pattern, correct. So, the Hamming distance between V and R is going to be the weight of this error pattern, and which we are denoting by t dash. Now, since V and W are valid code words, so the Hamming distance between V and W will be at least equal to minimum distance of the code. So, the Hamming distance between V and W is greater than equal to minimum distance of the code, and in the beginning we defined that our minimum distance is at least 2t plus 1. So, from these two we can write that Hamming distance between V and W is greater than equal to 2t plus 1. Now, from the triangular inequality we know that Hamming distance between R and W, this we can see from here, this relationship basically triangular inequality, what we have is the Hamming distance between V and W to be less than equal to Hamming distance between R and W plus Hamming distance between R and V, right. Now, this we can write as, we can bring this here and we can bring this here, what we can write this as, let us say we can write this relation in this particular form. Okay. Now, what is this quantity? Hamming distance between V and W. The Hamming distance of between V and W is at least equal to 2t plus 1. And what is the Hamming distance between the transmitted code word and the received code word? This is, we denote it by t dash. So, then Hamming distance between R and W is given by 2t plus 1 minus t dash. Now, as long as your error pattern is less than equal to t, the weight of the error pattern is less than equal to t, in that case the Hamming distance between R and W will be you can plug that value of t here, and what we will get is Hamming distance between r and w is greater than equal to t plus 1, which is greater than equal to t, whereas the Hamming distance between transmitted code word and the received code word is t hat, which is less than equal to t. What does it mean? It means that the received code word is closer to v than any other code word w. So, what will your maximum likelihood decoder for binary symmetric channel will decide in favor of? It will decide in favor of v. So, you will correctly decode this received sequence to be v, and this was our transmitted code word. So, you will not make an error. So, what we have shown here is, as long as your error pattern has weight up to t, those error patterns are correctable, provided the minimum distance of your code is d min and it satisfies this relationship. So, if minimum distance of the code is at least 2t plus 1 and it is less than equal to 2t plus 2, then it can correct all error patterns of weight t or less. So, as we can see here, the received code word is closer to v than any other code word w. So, it will decide in favor of v, and this r will be decoded as v. Next, we are going to show that if there exists an error pattern of weight greater than equal to t plus 1, then our decoder whose minimum distance is at least 2t plus 1, but less than 2t plus 2, this decoder will make an error. In other words, it would not be able to correct this error pattern of weight t plus 1. So, for all error patterns of weight L, if L is at least t plus 1, then our maximum likelihood decoder may not be able to correctly decode or correct that error. So, let us prove this. If v and w are two code words, and let us assume that the Hamming distance between v and w is equal to the minimum distance of the code, which is denoted by t min, and let E1 and E2 are two error patterns which satisfies these three properties. And what are these three properties? The sum of E1 and E2 is same as v plus w. The second property is E1 and E2, they do not have any overlapping ones. So, weight of E1 plus E2 can be written as weight of E1 plus weight of E2. And we will show that if there is an error pattern of weight L, where L is at least t plus 1, then our maximum likelihood decoder will make an error in decoding. So, the way we have chosen our error pattern, weight of E1 plus weight of E2 is given by weight of E1 plus E2, this is from 2, and from 1 we know E1 plus E2 is nothing but V plus W. So, this is same as weight of V plus W, and this is nothing but, this is Hamming distance between V and W, and we have said the Hamming distance between V and W is the minimum distance. So, this is equal to minimum distance. Now, let us assume that we transmitted this code word V and what we received is R. So, this V got corrupted by this error pattern E1, which has Hamming weight of at least t plus 1. Now, we will repeat the same exercise. We will try to find out the Hamming distance of this received code word from the correct transmitted code word V, and Hamming distance between the received code word and any other code word W. So, if we calculate the Hamming distance between W and the received code word, we know that Hamming distance between W and R is nothing but Hamming weight of W and R. And what is R? R is my received code word V plus E1. So, I can write this as W plus V plus E1. Now, what is W plus V? From 1, I have W plus V is same as E1 plus E2. So, then this is E1 plus E2 plus E1. So, E1 plus E1 will be 0. So, this will be E2, weight of E2. And what is weight of E2? From this relation we can see weight of E1 plus weight of E2 is d min. So, weight of E2 is d min minus weight of E1. So, this we can write as weight of E2 as d min minus weight of E1. So, d min is less than equal to 2t plus 1 and weight of E1 is at least t plus 1. So, weight of E2 will be less than 2t plus 2 minus t plus 1, which is t plus 1. So, the Hamming distance between W and R is less than t plus 1. And what is the Hamming distance between V and R? This is weight of E1. Okay. And what is weight of E1? Weight of E1 is given by L, which is at least t plus 1. So, what we have shown here is weight of W, Hamming distance between W and R is less than t plus 1, whereas Hamming distance between V and R is greater than equal to t plus 1. So, what we have shown is Hamming distance between W and R is less than equal to Hamming distance between received code word R and the true code word which was actually transmitted, which is V. So, in this case the maximum likelihood decoder will decode in favor of W and not V and will make a mistake. So, through this construction we have shown that if your error pattern is of weight t plus 1, then you are not guaranteed to correct that error. So, from this and the previous result we can conclude that if we have a block code with minimum distance d min, which satisfies the relationship that d min lies between 2t plus 1 and 2t plus 2, then this linear block code with minimum distance d min should be able to correct all error patterns up to weight t, where t is given by this. So, this t is known as random error correcting capability of the linear block code. Next, we are going to prove a result which is as follows. So, if we have an nk linear block code whose minimum distance is given by d min, then we can show where d min lies between 2t plus 1 and 2t plus 2, then we can show that all n tuples of weight t or less can be used as coset leader in our standard array. So, we are going to prove this result using method of contradiction. Now, let us say, so how does method of contradiction work? So, we will say, let us say they are all error patterns of weight up to t, let us say they are not coset leader. So, we will assume a scenario where there are two such n tuples with weight up to t which are not coset leader. In other words, they lie in the same coset or same row, and then later on we will show that that is not possible. So, that is how this method of contradiction will work. So, minimum distance of a code is d min. So, minimum weight of the code is also d min. Let x and y are two n tuples of weight t or less. Now, weight of x plus y will be less than equal to weight of x plus weight of y. Why? Because there might be some overlapping ones at some locations of this n tuple x and y, and we are given that the weight of x and weight of y is at most t. So, then weight of x plus weight of y will be less than equal to 2t, and this is less than minimum distance, because minimum distance of code is at least 2t plus 1. Now, let us assume that these x and y, which are error patterns of weight t or less, let us assume that they are not coset leader. So, if they are not coset leaders, let us assume they are in the same coset, they are in the same row. So, if we assume x and y are in the same row or same coset, then x plus y must be a code word. Why this is so? If you recall your standard array, we had something like this. First row, first column was all 0 vector, and then we had other code words, and then we had error pattern, let us say E2. So, this was E2 plus V2, like this was E2 plus V2k. Now, if you look at any two elements in the same coset or same row, and if you add them up, what do you get? Let us add this and this. What do we get? E2 plus E2 plus V2, we will get V2. If we add this and this, we will get V2 plus V2k, which is another code word Vs. So, if we take any two elements in the same coset and we add them up, we are going to get a non-zero code word. So, if x and y are in the same coset, then x plus y must be a code word. This is impossible. Why? If x plus y is a code word, then what is the minimum distance of x plus y? X plus y, minimum distance of that must be d min. But what is the weight of x plus y? We just showed in this bullet that weight of x plus y is less than d min. That means weight of x plus y is less than d min. If weight of x plus y is less than d min, then x plus y cannot be a non-zero code word, because the weight of a non-zero code word should be at least d min. So, our assumption that x and y are in the same coset is wrong. In other words, then x and y must be in different cosets, different rows, and we can always make these x and y as coset leaders. So, this proves our result that all n tuples of weight n of weight t or less can be used as coset leaders in the standard array, and we know that if we use them as coset leaders, those are our correctable error patterns. Next, I am going to show you a result which is as follows. So, if you have an nk linear block code whose minimum distance is d min, and if all n tuples of weight t or less are already used as coset leader, then there is at least one n tuple of weight t plus 1 which cannot be used as coset leader. So, this essentially is going to show us again the same result, that any weight pattern error pattern of weight t plus 1 is not guaranteed to be corrected. So, how do we prove it? So, let us assume V is the minimum weight code word of C, and we have two n tuples x and y, which satisfies these following conditions. First, x plus y is equal to V, and x and y do not have any component common. So, they do not have ones common in same position. So, from the definition, x and y must be in the same coset. Why? Because we know if two elements are in the same coset, and if we add them, the sum is a valid code word. So, if x plus y is equal to V, which is a valid code word, then x and y must be in the same coset. So, that is what I said, from definition x and y must be in the same coset, because x plus y is V, which is a valid code word, and we know that if we add any two elements in a coset, their sum is a valid code word. And similarly, weight of x plus weight of y is equal to weight of V, and we have chosen V to be the minimum distance code word. So, this is given by d min. Now, if we choose our y to have a weight of t plus 1, then we can see from here d min is greater than equal to t plus 1, but less than equal to 2t plus 2. So, from this, and using the fact that d min lies between 2t plus 1 and 2t plus 2, using these two results, what we get is weight of x can be t or t plus 1. So, therefore, if we choose x to be our coset leader, then we cannot choose y as our coset leader. You can see, because x and y are in the same coset, and weight of x is t or t plus 1, whereas weight of y is t plus 1. So, I will choose x as my coset leader, and if I choose x as my coset leader, then I cannot choose y as my coset leader, which proves my result, which says that if all n tuples of weight t or less are used as coset leaders, then there exists at least one error pattern of weight t plus 1, which cannot be used as coset leader. And if this error pattern of weight t plus 1 cannot be put as coset leader, then this is not a correctable error pattern. So, with this I will conclude my lecture on random error correcting and random error detecting properties of block codes. Thank you.